everyone and welcome to the latest installment of the IGCSE 0606 Solution Guide series. In this video we will take a closer look at paper 1.3 from the October-November exam period of 2020. So without further ado, let's get straight into it. In exercise 1a we are supposed to sketch the graph of the function y equals x minus 2 multiplied x plus 1 multiplied 3 minus x, stating the intercepts on the coordinate axis. As we can see, the function is stated in form of factors of a polynomial, meaning that it is very easy for us to figure out the 0 points of this function, which are 2, -1 and 3. As for either of those numbers, one of those factors would return 0 as a result. Secondly, to determine the y-intercept, we simply substitute all of our x's for 0. So our calculation is straightforward, being -2 multiplied 1 multiplied 3, which equals -6. In the last step, we need to expand this expression in order to determine the orientation of our graph. In step 1, we are multiplying the first two brackets with each other. In step 2, we simplify the expression within the newly created first bracket. In step 3, we will multiply and expand those two brackets, and after simplification we come to the conclusion that this function can be written as -x cubed plus 4x squared minus x minus 6. And since the coefficient of x cubed is negative, we know that this cubic function must have this specific shape, which means that its tangent has to be negative first, then being positive, and then negative again. Part B of exercise 1 requires from us to write down the values of x, such as x minus 2 multiplied x plus 1 multiplied 3 minus x is larger than 0. Taking a closer look at our sketch, we can figure out that this is true for all of the x values that are equal or less than -1 or between x positive 2 and 3. In exercise 2a, we are supposed to find the first derivative of the function y equals e to the power of 2x minus 3 over x squared plus 1. Since our argument x occurs in the numerator as well as in the denominator, we will have to employ the quotient rule for derivatives, which you are provided with to the right-hand side of your screens. To find the first derivative of the e function, we need to keep in mind that we will have to employ the chain rule here as well, which you can also find to the right-hand side of your screen, since our argument x here occurs in the power statement of this expression, meaning that we will have to find the first derivative of 2x as well, which equals 2. Simplifying this entire expression provides us with the solution that the first derivative of the given function equals 2e to the power of 2x minus 3 multiplied by x squared plus 1 minus 2e to the power of 2x minus 3 multiplied x over x2 plus 1 squared. Part B of exercise 2 follows up on our result of part A, stating that given that y is increasing at the rate of 2 units per second, we are supposed to find the exact rate of change of x when x equals 2. So to do that, we simply enter 2 into the first derivative of our given function, and with the assistance of our pocket calculators we should come to the conclusion that this results in 6e over 25. Now to find the rate of change for y equals 2, we just multiply our previous result with the expression dx over dt and equal it with 2, and rearranging this equation for dx over dt will result in the rate of change for y equals 2 being 25 over 3e. Next on to exercise 3. In part A we are provided with the function 4 multiplied the natural logarithm of 2x minus 1, and in part A of this exercise we are supposed to write down the largest possible domain for the function f. Since the domain for natural logarithms is x larger than 0, we need to ensure that this is true for the expression within the brackets, so we need to assure that 2x minus 1 is larger than 0, and rearranging this inequality delivers the result that this is true for every x that is larger than 1 over 2. In part 2 of exercise 3a, we are required to find the inverse function of f of x as well as its domain. To accomplish the first part, we simply reverse y and x with the goal to rearrange the equality for y. This can be achieved in isolating our natural logarithmic expression, which is achieved by firstly dividing both sides of the equation by 4. Secondly, employing the basic laws of logarithms, which you can find to the right-hand side of your screen. We will free ourselves ourselves from the natural logarithmic expression, keeping in mind that the inverse of the natural logarithm is the e function. Finally, we add both sides of the equation with 1 and divide then everything by 2, which provides us with the result that the inverse function equals e to the power of x over 4 plus 1 over 2. The domain of the inverse of our function is the entire realm of the real numbers, since e functions are defined for all x's within this domain. In part B of exercise 3, we are provided with two functions, g and h. G of x equals x plus 5 for x being element of the real numbers, and h of x equaling the square root of the expression 2x minus 3 for all x's equal or larger than 3 over 2. We are required to solve g of h of x equals 7. Here we are dealing with a compound function, which mechanisms you will be provided with on the right hand side of the screen. So what we simply need to do is to substitute x of the g function with h of x, after which we receive the equation the square root of 2x minus 3 plus 5 equals 7. In step 1 we will isolate our root expression, after which we square both sides of the equation, isolate x, and then in a final step divide both sides of the equation by 2, which results in x equaling 7 over 2. Next on to exercise 4. In part A we are provided with a diagram that shows the xt graph for a runner, where displacement x is measured in meters and time t in seconds. In part 1 of the exercise it states that on the axis below we are supposed to draw the vt graph for the runner. We should know from physics that displacement and velocity are related, such as that the first derivative of our displacement will provide us with the velocity, and that therefore the gradient between the intervals needs to be determined. So in this case our intervals go from 0 to 50, from 50 to 65, from 65 to 85, and finally from 85 to 125. The formula on how to calculate all of these gradients can be found to the right hand sides of your screen. Thereafter we will insert our results accordingly into the vt graph. So for the interval of t between 0 and 50 we will insert the constant 2. For the interval of t between 50 and 65 seconds we will enter the constant line 0. For that of between 65 and 85 seconds it will be 2.5, and accordingly for our final time interval it will be negative 3.75. Part 2 of exercise 4a requests from us to find the total distance covered by the runner in 125 seconds, and for that we need to simply examine the area between the vt graph and the x-axis, which in this case are just areas of squares that need to be added up. So to determine the area of the first rectangle we just need to multiply 2 by 50, add this with 2.5, multiplied the difference of 85 and 65, and this in return needs to be added up by 3.75, multiplied the distance between 125 and 85. After simplifying this equation, we can conclude that the total distance covered by that runner for the first 125 seconds of his race is 300 meters. Exercise 4b states that the displacement x meters of a particle from a fixed point at time t, s, is given by the function x equals 6 cosine 3t plus pi over 3. We are required to find the acceleration for the particle when t equals 2 pi over 3. The relationship between displacement and acceleration is as follows. The second derivative of displacement delivers us the acceleration of that particle. So what we first need to do is to differentiate our function twice, and to do that we need to employ a combination of rules of derivatives, namely the rule of derivatives for trigonometric functions, as well as the chain rule, since our argument t occurs within those brackets. 6 is just a factor which remains after differentiation. The derivative of cosine is negative sine, and the derivative of 3t equals 3. Simplifying this expression will lead us to the result of the first derivative of the function, which is negative 18 sine of 3t plus pi over 3. Applying the same rules for the second derivative provides us with the final result of negative 54 cosine of 3t plus pi over 3. To To now calculate the acceleration of the particle at t equals 2 pi over 3, we just replace t for 2 pi over 3 in our second derivative, which brings us to the conclusion that the acceleration at the time 2 pi over 3 equals negative 27 seconds per meter squared. Next on to exercise 5. Here it is stated that given that the coefficient of x squared in the expansion of 1 plus x multiplied 1 minus x over 2 to the power of n is 25 over 4, and we are supposed to find the value of the positive integer n. In order to expand this factor, 1 minus x over 2 to the power of n, we will have to employ the binomial theorem, which you can find to the right hand side of your screen. The calculation of this expression can be halted once we encounter x squared. Since 1 multiplied this expression and x multiplied the second summand provides us with all of the coefficients that would occur in relation to x squared. Consequently, the first summand within this expression can be neglected, since 1 multiplied 1 equals 1 and x multiplied 1 equals x, so none of which provides us with a result that relates to x squared. We are getting the first summand of the equation after multiplying x with n choose 1 multiplied negative x over 2, and the second summand in multiplying 1 with n choose 2 multiplied x over 2 squared. From there we divide x squared from both sides of the equation. According to the binomial theorem, the expression n choose 1 can be rewritten in this way. Again, you can take a look at it at the right hand side of your screens, and the expression n choose 2 is transformed accordingly as well. To simplify all of the denominators of this equation, we will multiply each side of it with 4. So 4 divided by 4 equals 1. And 1 over 2 divided by 2 equals 2. At this stage we will again simplify our denominators. 2 factorial equals 1 multiplied 2, which equals 2. Thus we will multiply both sides of the equation with 2. So now what we are left with concerning the denominators of this equation are the expressions n minus 1 factorial and n minus 2 factorial. And to eliminate those, we'll have to rewrite our numerators, which is n factorial in both cases. To achieve that, we will take a look at the first and the last 3 factors of this product, meaning that n factorial equals to 1 multiplied 2 multiplied 3, which represent the first 3 factors, and the final 3 would accordingly be n minus 2, n minus 1, and n. Thus, n factorial can be rewritten as the expression n minus 1 factorial multiplied n, but also n minus 2 factorial multiplied n minus 1 multiplied n, which we can find in the numerators of the first and second summand of this equation respectively. Now we can just simplify both of our fractions, and we are left with the expression that negative 4n plus n minus 1 multiplied n equals 50. We are expanding the product n minus 1 multiplied n and further simplify our equation down to the expression n squared minus 5n minus 50 equals 0. This equation can now be solved with the help of the rule for quadratic functions, which you're provided with on the right hand side of your screen. Inserting all of our coefficients accordingly into the formula, we will receive 2 results, one being negative 5, which is not defined since we're supposed to find the value of the positive integer n, and the second one being 10, which according to the constraints of this exercise is a valid solution. Next on to exercise 6. Here it is known that y equals a multiplied 10 to the power of bx squared, where a and b are constants. When the logarithm of y with base 10 is plotted against x squared, a straight line passing through the points 3.63, 5.25 and 4.83, 6.88 is obtained. In part A of this exercise, we are supposed to find the value of a and b. Solving this equation entails the application of using the basic laws of logarithms, since we are dealing with an exponential function. Since our base here is 10, it is best to solve this equation using logarithms with base 10. Thereafter, we receive the expression that the logarithm of y with base 10 equals the logarithm of a with base 10 plus bx squared. From here, using our points that are provided in the exercise, we can set up a system of equations which will help us to obtain the values for a and b. So we simply replace the y values of our points for y and their x values for x squared respectively, since the logarithm is plotted against x squared. To solve this system of equations, we will rearrange the first equation for the logarithm of a with base 10 and substitute this expression for the logarithm of a with base 10 in the second equation. Doing so will eliminate a, and from there, by rearranging to b, will deliver us the value for it, which is 1.36. 1.36 can then be substituted for b in the first expression, which leaves us with the result that the logarithm of a with base 10 equals 0.313. And similarly to the start of our exercise, we will have to solve this exponential function with the application of the basic laws of logarithms. After applying this method, we are able to conclude that the value for a equals 2.06. In part b of this exercise, we are supposed to use our values of a and b to find the value of y when x equals 2. To achieve that, we will again take a look at our original exponential function, replace a for our result that we have determined in part a of this exercise, and replace x for 2 as mentioned in this exercise. The value for b is also substituted accordingly with 1.36. Putting all of this into our pocket calculators will help us to determine the value of y, which is 567,371.11. Part C of exercise 6 demands from us to find the positive value of x when y equals 4, so x should be larger than 0. So in this case, we will again take a look at our original exponential function and replace all of the values accordingly, and in this case we will replace y with 4 while x has to be determined. So this here will be the setup of our equation. Firstly, we are applying the laws of exponents to simplify this expression and convert it into the expression 10 to the power of 3.6 x squared, and also divide both sides of the equation by 2.06 in order to isolate x. So here again, similarly to the start of this exercise, you will have to use the basic laws of logarithms in order to solve this exponential equation. From here we just isolate x squared in dividing both sides of the equation by 1.36, and after figuring out the square root of x squared, we will pick only the positive solution for x as per the requirements of the exercise and come to the conclusion that x equals 0.46. Moving on to exercise 7, the polynomial p of x equals ax cubed plus bx squared minus 19x plus 4, where a and b are constants, has a factor x plus 4, and is such that 2 multiplied p of 1 equals 5p of 0. In part A, we are supposed to show that p of x equals x plus 4 multiplied ax squared plus bx plus c, where a, b, and c are integers to be found. So to approach that task, we will firstly set up the equation that is provided within the exercise, and on the left hand side replace x for 1, which gets us the expression 2 multiplied a plus b minus 19 plus 4, and on the right hand side of the equation we will set x 0, which leaves us with 4. In a second step we will simplify the equation by multiplying 5 with 4 and dividing both sides of the equation by 2, and from there we will rearrange the equation for b. Rearranging the equation for a is also a possibility. Picking b is just a personal preference of mine. In step 2, we will make use of the statement that this polynomial has a factor x plus 4, which just means that p of negative 4 equals 0. Since for x negative 4, this curve would intersect the x-axis. So we are replacing negative 4 for x, which then in return provides us with the equation negative 64a plus 16b plus 76 plus 4 equals 0. And again, we will just simplify this equation and rearrange it once more for b, as in the first part of this exercise, and receive that b equals 4a minus 5. From there, we can now set up a system of equations in order to determine the value of a. So 25 minus a equals 4a minus 5, since both expressions represent b, and in doing so we have eliminated the variable b and are only left with the variable a. Rearranging this equation for a lets us conclude that the value for a is 6. Inserting a either into this or that equation on top will provide us with the conclusion that b equals 19. Now that we know that the value for a equals 6 and for b 19, we simply replace a and b for their values and perform a long division in order to determine our values for capitalized factorized a, b, and c. And applying the long division for the function 6x cubed plus 19x squared minus 19x plus 4 divided by x plus 4 equals 6x squared minus 5x plus 1. Thus the integers for capitalized a, b, and c equals 6, -5, and 1. In part B of exercise 7, we are supposed to factorize the function p of x. Since the first factor has already been given in the exercise, we just need to focus on the factor ax squared plus bx plus c and find the solution of it for 0. This can be accomplished in using the rules for solving quadratic functions, which are provided with to the right-hand side of your screen. Applying this method provides us with two additional factors, namely 1/3 and 1/2. Now we need to convert those solutions into factors, which is done by changing their signs within those brackets. For a better look, we can multiply those factors with the denominator of the fraction, which provides us with a more pleasing look. So 3 multiplied x equals 3x, 3 multiplied 3 of course 1, and similarly here 2 multiplied x equals 2x, and -1/2 multiplied 2 equals -1. In the final part of this exercise, we should find the remainder when the derivative of p of x is divided by x. So in step 1, we need to find the derivative of p of x, which can entirely be accomplished by using the power rule combined with the sum rule for derivatives, which you are provided with to the right-hand side of your screen. So here we should get the result that the first derivative of p of x equals 18x squared plus 38x minus 19. And it should be evident that we can only divide the first two summons, 18x squared and 38x by x, which leaves us with the remainder of -19. Next on to exercise A, where we are provided with a diagram that shows the figure ABC. The arc AB is part of a circle, center O, radius r, and is of length 1.4 r. The point O lies on the straight line CB, such that CO equals 0.5 r. In part A of this exercise, we are required to find in radians the angle of AOB in radians, which can be done applying the formula that you're provided with to the right-hand side of the screen. From there, it should be obvious that the angle AOB in radians equals 1.45 r. Forward to part B, here it states that we should find the area of ABC, giving our answer in the form kr squared, where k is a constant. So to calculate the entire area of ABC, we will subdivide the area into two portions, portion 1 being this sector, and portion 2 the triangle ACO. The sector can be calculated using the proper formula that you can encounter on the right-hand side of your screen, and after inserting all of our numbers properly into it, we should conclude that the area of the sector is 0.725 r squared. In a second step, we will determine the area of the triangle ACO. Since AOB is a sector, we can conclude that the distance between O and A is the same than that between O and B, thus this length will be r. We are also provided with the distance between C and O, which is 0.5 r, as well as with the portion of this angle, which can be calculated with the help of our result from part A of this exercise, for which we just have to subtract 1.45 from pi. The area of this triangle can now be determined using the formula for SAS triangles, SAS standing for side, angle, side, which you can find on the right-hand side of your screen. Employing this formula will let us conclude that the area of this triangle is 0.248 r squared. And now, since we have calculated both portions of the area, we just need to add up our results in order to learn the size of the entire area ABC, which will lead us to the result of 0.973 r squared. Part C of exercise A states that given that the perimeter of ABC is 12 centimeters, we are supposed to find the value of r. So what we already know is the distance between A and B, which is 1.45 r, as well as the distance CB, which is 0.5 r plus r, which means 1.5 r in total. What is left for us is to determine the length of AC, the length of AC. For this, we will once again be operating within this triangle. And since we are still operating within a triangle where we are provided with two sides that enclose an angle, We will be using the cosine formula to determine the distance between A and C, which you will be provided with to the right hand side of your screen. After inserting all of the values accordingly into the formula and simplifying the equation, we will arrive to the conclusion that AC equals 1.17r. So now with that piece of information, we will finally be able to find the value for r. So we can equate 12 with the length of AC plus the length of AB plus the length of CB. And rearranging this equation for r will provide us with the result that r equals 2.91 centimeters. Next, over to exercise 9, where we are presented with a diagram that shows the triangle OAC. Point B is the midpoint of the line OC. The point Y lies on AC such that OY intersects AB at the point X, where AX over XB equals 3/1. It is given that the vector OA equals A and the vector OB equals B. In part A of this exercise, we are supposed to find the vector OX in terms of A and B, giving our answer in its simplest form. Since X is located on the line AB, we will first take a look at how to represent the vector AB in terms of A and B. And to get from A to B, we just travel from A to O and from O to B. Since the vector OA is represented by A, the opposite direction from A to O is thus represented by negative A, and OB can simply be replaced with B. Thus our vector AB can be represented by the expression negative A plus B. Additionally, the exercise states that AX over XB equals 3/1, which is represented by the line from A to B and the corresponding numbers 3 and 1, which I've inserted into this diagram. So what we can tell from this is that the entire length from A to B consists of a total of 4 parts, 3 plus 1. So now to get from O to X, we will travel from O to A and from there to X. The vector AX can be represented by the expression 3/4 x multiplied vector AB, since the distance between A and X consists of 3/4 of the part of the distance from A to B. Vector OA can then be substituted by the expression of A, and vector AB can be substituted by the expression negative A plus B. Simplifying this expression allows for us to conclude that vector OX can be represented by the expression 1/4A plus 3/4B. Part B of exercise 9 requires from us to find vector AC in terms of A and B. This can be achieved by traveling from A to O, from there to B, and finally from B to C. All of those parts are already known in terms of A and B for the following reasons. To get from A to O, we need to travel negative A, since we are traveling into the opposite direction of A. To get from O to B is straightforward, since vector OB is already represented by B. And we can also deduce from the sentence that the point B is the midpoint of OC, that the distance from B to C is equal to the one from O to B, which is B, and since we are also traveling into the same direction, vector BC can be represented by B. Simplifying this expression presents us with the solution that vector AC can be represented by the expression 2B minus A. Part C of exercise 9 states that given that the vector OY equals h multiplied the vector of OX, we are supposed to find vector AY in terms of A, B, and H. Considering the statements that we are presented with in this part of exercise 9, there's only one way to approach this exercise, which is by getting from A to Y via O, which means negative OA, which is the same as vector AO equals negative A, and from there we are required to travel from O to Y over X, which is represented by the expression h multiplied OX. What's left for us to do is to figure out a way to find vector OX in terms of AB, which we have already achieved in part A of this exercise, so we can just copy over our result over into this expression. Thus vector AY can be represented in terms of A, B and H via the expression negative A plus H multiplied 1/4A plus 3/4B. Part D states that given that vector AY equals M multiplied vector AC, we are supposed to find the value of H and M. So in the first step, we will simply represent the vector AY by our previously calculated result and try to find a way to represent vector AC in terms of A and B first, which we have previously done in exercise 9b. From there we will expand the expression within the brackets on both sides of the equation, and from there factorize the expressions on both sides of the equation for as much as possible in terms of a and b. After having done that, we can see that negative a multiplied the expression within the brackets plus b multiplied with this expression within the brackets equals to something that looks very similar on the right hand side, the only difference being the expressions within the brackets, but with negative a plus b being equal. Since this is the case, this means that 1 minus h over 4 equals m, and at the same time 3h over 4 equal 2m. So from here on we are provided with the system of equations which should help us in finding the values for h and m. In order to firstly calculate h, we will substitute m in this expression for 1 minus h over 4, since this also equals m. And after doing that, we will rearrange this equation for h, which at the end should deliver us that h equals 8 over 5. To now determine the value for m, we can simply substitute h for 8 over 5. And after doing so, using our pocket calculators, we should arrive at the conclusion that the value for m equals 3 over 5. Moving on to exercise 10. In part A, we are supposed to show that the expression 1 over x plus 1 plus 2 over 3x plus 10 can be written by the expression 5x plus 12 over 3x squared plus 13x plus 10. So this is done by firstly finding the common denominator of those two fractions here, which can be done by performing a cross multiplication. So we will multiply the numerator of the first fraction with the denominator of the second one, which equals to the expression 3x plus 10. And secondly, we will multiply the numerator of the second fraction with this 2 with the denominator of the first fraction x plus 1. As for the denominator, we just multiply the denominators of the two fractions with each other. After firstly expanding the numerator and denominator and simplifying the expressions in both of them, we should come to the conclusion that the expression 1 over x plus 1 plus 2 over 3x plus 10 can indeed be written as 5x plus 12 over 3x squared plus 13x plus 10. In part B of exercise 10, we are presented with a diagram that shows parts of the curve y equals 5x plus 12 over 3x squared plus 13x plus 10, as well as with the line x equals 2 and a straight line of gradient 1. Furthermore, the curve intersects the y-axis at point P. The line of gradient 1 passes through P and intersects the x-axis at point Q. We are supposed to find the area of the shaded region, giving our answer in the form a plus 2 over 3 multiplied the natural logarithm of b multiplied the square root of 3, where a and b are constants. So what we need to do in the first step is to find the function that represents the line that goes through Q and P. What we are already provided with is the fact that the gradient of this line equals 1. We already know that the x-coordinate of point P is 0, since the curve intersects the line in point P, meaning both of them share this point. So after setting x0 within this function, we are left with the expression of 12 over 10, which can be simplified to the expression of 6 over 5. Thus the coordinates of point P is 0 and 6 over 5. Next, we need to determine the coordinates for our point Q, and here we are already aware of the y-coordinate, which must be 0, since Q is located on the x-axis. So now determine our value x. We simply replace y with 0, using the general linear function for straight lines. M represents the gradient, which according to this exercise is 1, and B represents the y-intercept, which we have just calculated at being located at 6 over 5. From there we simply rearrange this equation for x, and we should arrive at the conclusion that the x-coordinate for Q is negative 6 over 5. So now that we are aware of all of these points, we can easily calculate the area of this triangle, which can be done using the formula for calculating the area of right triangles, which you are provided with to the right hand side of the screen. So we now know that the distance from O to P equals 6 over 5, and the same accounts for the distance between O and Q. So inserting all of those values into our formula should help us in coming to the conclusion that the area of the triangle PQO equals 18 over 25. To calculate the remaining part of the shaded area, we will have to integrate the function of the curve within the boundaries of 0 and 2. In order to simplify the integration process, we will make use of our knowledge from part A of this exercise, which states that the expression of this function can be represented by the sum of those two fractions. And this will enable us by employing the reciprocal rule for integrations, which you are provided with to the right-hand side of the screen. So what is required here is the integration of each of those summands separately, which is also in accordance with the rules of integration. And from there we simply insert our boundaries for x and subtract both of those expressions from one another. We should keep in mind that ln1 equals 0 and that after eliminating our brackets, we need to invert all of the signs inside of it, which means that this plus sign will be converted into a negative sign. Additionally, the second and the third summand here both have the same coefficient, being 2 over 3. So at this stage we can almost factorize this entire expression. The only missing link is that the coefficient of the first summand is 1. You might ask yourself why it is desirable to factorize 2 over 3 ln. The reason for that is that the exercise states that we must give our answer in the form a plus 2 over 3 ln, and this is the only way to fulfill this requirement. This can be manipulated using the basic rules of logarithms, which you're provided with to the right hand side of the screen. So we can use the same coefficient here, but we need to balance it in using the power of 3 over 2, since according to the basic laws of logarithms, the expression 3 over 2 multiplied 2 over 3 ln 3 can be rewritten as 2 over 3 ln 3 to the power of 3 over 2. The logic behind this is that we actually do not change the expression ln 3 at all, since we are just multiplying it with 1. Since 3 multiplied 2 equals 6, 2 multiplied 3 equals 6, and 6 over 6 equals 1. So the only thing that we are using here is a technique in order for us to find a way to factorize the expression 2 over 3 ln, which is done in this step here. Additionally, again according to the basic rules of logarithms, which you will be provided with to the right hand side of the screen, the addition of the same logarithms can be simplified into multiplications, and corresponding subtractions can be simplified into divisions. So at this stage we encounter the expression of the square root of 3, which is also part of the requirements according to the exercise. So the only thing that we need to do is to simplify everything else, which will represent our b. So 3 multiplied 16 equals 48, and the expression 48 over 10 can be simplified to 24 over 5. So now that we have calculated the area between the curve and the x-axis for the interval between 0 and 2, we simply add it up with the previously calculated area of the triangle, which then equals to 18 over 25 plus 2 over 3 ln 24 multiplied the square root of 3 over 5, which is in accordance to the requirements of our exercise. We have now arrived at the final exercise of this exam paper, which is exercise 11. In part A of this exercise, it is given that 2 cosine x equals 3 tangent x, and we are supposed to show that the expression 2 sine x squared plus 3 sine x minus 2 equals 0. So firstly, we need to find a way to convert our cosine and tangent expressions into expressions in terms of sine. So according to the trigonometric identities for sine, cosine and tangent, we can convert the expression 3 tangent x into the expression 3 multiplied sine x over cosine x, which you can see on the right hand side of your screens. From there we multiply both sides of the equation with cosine x, leading us to this expression here. Now using the trigonometric identities according to Pythagoras' theorem, which you can also find on the right hand side of the screen, we can rewrite the expression cosine x squared to 1 minus sine x squared, and then expand the expression 2 multiplied 1 minus sine x squared, which leads us to this expression. And after that we will simply rearrange this entire equation for 0, which makes sense since we are supposed to find an expression that equals 0, and come to the conclusion that indeed the expression 2 multiplied sine x squared plus 3 sine x minus 2 equals 0 is the equivalent of the expression 2 cosine x equals 3 tangent x. In part B, we are supposed to solve the equation 2 cosine 2 alpha plus pi over 4 equals 3 tangent 2 alpha plus pi 4 for 0 less than alpha less than pi radians, giving our answers in terms of pi. We should realize that this equation is very similar to the one above in part A of this exercise, the difference being that x is replaced with our expression within the brackets. So it would make entire sense to make use of the relationship that was determined in exercise 11a in order to help us to find a solution for sine x. So this setup here pretty much resembles what we can see in part A of exercise 11. From there we divide both sides of the equation by 2. In the second step we will complete the square of this quadratic function, which formula you are provided with to the right hand side of the screen. Continuing from there we will isolate our quadratic function and transfer everything else to the right hand side of the equation, and all of this here belongs to our quadratic function. From here we just need to take the square root on both sides of the equation, and yes, when we take the square root of a positive number we receive two solutions, but in this case only positive solutions will be taken into consideration in accordance with the fact that alpha is supposed to be larger than 0 and less than pi, which is only given for 5 over 4 but not for negative 5 over 4. In the final step we rearrange the equation for sine, which provides us with the result that sine 2 alpha plus pi over 4 equals 1 over 2. Again, imagining that this expression within the brackets resembles x, we can find out with the help of our pocket calculators that sine x equals 1 over 2 in radians equals pi over 6. So from here, looking at the first couple of solutions, which we can determine with the help of our pocket calculators, we will investigate what happens for x equals pi over 6, 5 pi over 6 and 13 pi over 6. Therefore, we will equal those possible solutions with this expression within the brackets 2 alpha plus 4 pi. So equaling this with pi over 6 will lead us to a result which is less than 0, which is not a solution according to the requirements of this exercise. Moving on to our option 5 pi over 6. After rearranging and simplifying this equation for alpha, we come to the conclusion that in this case alpha would have the value 7 pi over 24, which is meeting the requirements of the exercise, since 7 over 24 is between 0 and pi. Our next option to consider is 13 pi over 6, after which we come to the conclusion that alpha in this case would contain the value 23 over 24 pi, which is just underneath pi, which would be 24 over 24 pi. Thus we don't need to further investigate any solutions past 13 pi over 6, since this certainly would extend the range of our interval. I've been your host Marco from Planet Maths. Should you derive any value from my videos, please consider to leave a like, comment and subscribe. Thank you for watching. Cheers.